Oh, the webinar's just been started.
The session this afternoon. My name's Ahmed. I'm part of the event team here at Alpha Events, and I just wanted to introduce this panel and hand over firstly to Christopher from Zapata, who will be introducing the rest of the panelists, and then begin the panel over from his side. So over to you, Christopher.
Thank you very much, Ahmed, and thank you to QTech for having us and hosting this panel today. We're going to talk about the title you see in front of us, quantum sampling, which we believe is the fastest path to quantum advantage, actually, in real practicality in production. And I'm here today with Sonika Johri from IonQ and Eric Reuthe from our organization from Zapata. And they'll each give their introductions at their proper times when we go along. So next slide. We're going to talk about how we get to quantum advantage, and we want to do this in a way that those of you who are on the technical side and those of you who are from the quantum community can feel that we're doing this in a way that's actually has a good theoretical basis behind it, and that we're not just hyping or talking about things that are seem quantum but they're not, or this kind of thing, because we really want this to be scientifically valid in the community, what we're talking about here, because it does have really good theoretical underpinnings. But to do that, it requires a little bit of peeling an onion here into different layers to get you to why we think that there's really theoretical quantum realness to why we're seeing the results that we are. So next slide. So it starts, the first layer of the onion, I guess, starts with the quantum supremacy experiment. Many of you will have known about this. It was announced to quite some fanfare in late 2019, this paper by the Google team. Basically what happened here was Google were able to on their team show, and with a really good theoretical proof of it, that empirically on an experimental system with a 53 qubit system, they were able to do this random parameterized circuit experiment that showed that they could do something in 3 minutes that would take, depending on whose estimate you believe, 10,000 years or maybe 3 days, but something longer, much longer, and intractably longer on a classical computer, on Oak Ridge's supercomputer, compared to what they could do on this machine, and with a lot lower energy cost, actually, to be able to do that, which is significant. So that was an experimental empirical quantum advantage. But the key here, and this is what you have to keep in mind, is that they're doing something random here. So they had a source of randomness that was in a regime at 53 qubits that a classical computer could not achieve. And that's really the key underlying thing. So keep that in mind, the randomness and being able to do something, this randomness task, if you will, in a way that was not replicable easily on a classical computer. So next layer of the onion. So where can we use randomness in computer science, in stuff that we do in production today? Well, neural networks require randomness, actually, in the way a lot of these neural network architectures work, particularly in things like generative modeling. You start with an initial distribution. What is that? That's a random distribution chosen randomly, some source of randomness that feeds into your model. And you iterate and iterate and iterate until you find a distribution that fits your data, basically. That's kind of sort of the oversimplified way of thinking about how this works, a dumbed down explanation, no doubt. But that's really what we do. So we rely on some random bit stream to start. So what is your source of that randomness? Well, that makes a big difference. So the proposition on this layer of the onion is, okay, what if we had a parameterized tunable source of randomness, which is what we use in neural network construction for these tasks, that's quantum randomness and is quantum in its properties? Would that give us something better, different in doing neural networks, in doing machine learning? Wouldn't that be great? Well, we do know that we can do randomness from the Google experiment in a way that's intractable classically, but is it any better for any practical task? The Google task, random circuits, and then trying to simulate those wasn't very practical. But if you could use that source of randomness in a quantum distribution, perhaps that could be very useful in this practical application, which is machine learning. Next. So the idea would be that, well, can you find correlations in your data using that distribution and detecting that distribution in your data that have correlations that are a superset of what you can see classically? And if that's the case, then you will have something that is in a regime that is superior practically, but also superior in the sense of having an advantage over classical systems because of the nature of those numbers, the nature of those distributions. And what's even cooler about that is if it is better to use this quantum source of randomness in your neural networks, next slide, we can prove that it's quantum, and we can prove that it's quantum in its nature, because by looking at a distribution, we can calculate whether it is violating the Bell inequality. For example, that's one way that we can actually calculate and say that, yeah, no, this distribution could not be produced from a classical source. And if that's the case, then we really have connected the dots here at this layer of the onion. We're saying that we're using something that is provably mathematically, from a mathematical theory basis, quantum in its nature. It's not classically driven, and it is part of a superset of data that helps us find correlations in our data that are not tractable or calculatable in some normal time frame that would be practical on a classical computer, even a supercomputer. So that really connects all those layers of the onion. Next. And so if you could do that, well, where could we do better neural networks with classical data using this quantum distribution source? Well, Sonika is going to talk to you about one example of us actually doing this. So this is not a question we can actually do, and we can prove that it is actually better and that it's coming from an actual quantum machine, an actual quantum source. But if you can do that, we're going to show you something that's very visual and easy to understand and kind of cool. But I hope that the audience can abstract that too and extrapolate that too, where you could actually use this technology in real life problems, things like portfolio management, patient feature selection, manufacturing process selection, flow optimization for chemical processes, logistic networks, these kind of things that we're listing up here. There are actual industrial ways that we can use machine learning using classical architectures today in production that could benefit from this additional quantum boost and advantage that we're going to be able to do. Next. And I'll hand it over to Sonika.
Thanks, Chris. Hello, everyone. I'm Sonika Johri from IonQ, and I will be talking about the results from a collaboration between Zapata and IonQ, where we use the power of quantum sampling to enhance the generation of synthetic images. So let's begin. On the left here, you see pictures of human faces. However, these are not pictures of real people, but have been generated by what is known as a generative adversarial network. Such images are often also known as deepfakes, since they look extremely real, but they are in fact synthetic. Next, in the middle over here are real images of handwritten digits from what is known as the MNIST data set, which is a standard data set used for benchmarking many machine learning algorithms. The question we set out to answer here is whether we could enhance classical generative adversarial networks with NISQ quantum computers in the area of image generation. In particular, can we generate handwritten digits with the help of a quantum computer that are indistinguishable from the real images in the MNIST data set? This has been attempted before. On the right here is the most recent attempt in image generation with a quantum computer before our work. And you can see that it clearly has a way to go before it starts resembling the images in the center. Here, I'm showing you the basic architecture of the learning model, which is known as a generative adversarial network. Samples from a prior distribution shown here on the left are used as an input to a generator, which is a neural network. The generator then attempts to produce images that look like images of digits. These are then sent to another neural network, which is called a discriminator, which is trying to win a game where it can successfully classify the images from the generator as false, while at the same time classifying images from the real data as true. In a classical learning model, instead of using a fixed prior distribution, one can use what's called a born machine, which also evolves during the learning process in order to generate the prior samples. Well, since we're working with quantum computers, instead of using a classical born machine, we can instead use a quantum circuit born machine to do the same thing. That is to learn the optimal distribution for the prior. Here, a quantum, sorry, my PC just did something, but here a quantum circuit is initialized with random parameters. A measurement from the random circuit results in a bit string, which is used as an input to the generator. Each iteration in the learning algorithm leads to an update in the parameters of the quantum circuit until the generator and the discriminator reach an equilibrium where the generator is fooling the discriminator about 50% of the time. We expect to see quantum advantage here because the quantum circuit can in principle sample efficiently from distributions that are hard for classical computers. In fact, this was the basis of the quantum supremacy experiment from Google as well. However, in that experiment, the quantum sampling was not put to use in a real application, whereas here it is used in a hybrid quantum classical learning architecture. We tested this idea on quantum hardware from IonQ. For this experiment, we used 8 qubits of the 11-qubit quantum computer from IonQ that is available on the cloud. On the left over here, you see a comparison of how the learning evolves on the quantum hardware, which is shown in orange, versus how the learning evolves with a purely classical model, which is shown in black. The inception score plotted on the y-axis over here is a measure of how realistic the images look, as well as whether all of the digits are produced with roughly equal probability. On the right here, you see images from the generator in the hybrid quantum classical model when the learning has just started. You can see that as the learning progresses, the images generated get more and more realistic until they are
We're having a little bit of a technical thing. In the meantime, if people have questions, also you can post them on the Pathable platform in the chat box.
Okay, I'm back. Sorry, my computer just did something. I'm so sorry about that. Is everyone still here? Can people hear me? Yes. Okay. So I was just talking about how as the learning progresses, the images generated get more and more realistic until they're practically indistinguishable from real images. And finally, we see that the learning model that utilized the quantum computer outperforms the purely classical model. This is really exciting since this shows that quantum sampling can be useful even for NISQ computers. I also want to note here that this experiment was actually done on the previous generation of IonQ's quantum computer. The new generation of IonQ's quantum computers have more qubits and much higher fidelity gates. And when they're coupled with learning schemes, such as the innovative ones that Zapata is designing, they can actually take advantage of quantum randomness very soon, and we can start applying those to real-world applications in a short time frame. And I will hand it over to Eric now.
All right.
Thank you.
Thank you, Sonika. I'm Eric Reuthe. I'm the VP of Engineering here at Zapata, and I'm not a scientist. I'm a software engineer, so I'm focused on the practical application of a lot of this research. And so I've really been looking at what it takes as far as tools and strategy to really utilize some of this quantum technology in an enterprise. And we can go to the next slide, Sonika. Thank you. So what would a solution look like in practice? So, moving just beyond the research to real everyday use of quantum, it's going to look very similar to what we do with, current machine learning with some added dimensions. But here you can see, we have the possibility of having our model being driven by messages that could be constantly coming in, data streams. Obviously, in many cases, we're dealing with a large volume of data, and our computational tasks can be very intensive prior to even running a quantum circuit. And so we may have our computational workflow and also offloading some of the data pipeline activities to say an HPC cluster or even a supercomputer in some cases. Next, please. And this can get even more complicated if we look at the infrastructure possibilities. So, right now, hardware access is through the cloud. Eventually, it will be on-prem. But we also may want to utilize current on-prem infrastructure, especially if an organization already has an investment in HPC or supercomputing resources, and of course, working with the major cloud services as well. So we could have any combination of these infrastructures. Next, please. And so there's also a lot of kind of invisible requirements that shape your solution, because we are talking about running these things in an enterprise. And we need to be concerned with security, overall governance in some industries, compliance and regulatory, overall operations. So we need to be able to scale our solutions, make sure that they're highly available, reliable, and have deployments automated. And then, of course, there's data management issues as well. Storage, privacy, and actually architecting the data. These all come into play in developing a solution. And this is one of the things that we're focusing on is trying to address these issues on the front end. So when we have research that is done and has great practical application, and in the future, when we've got powerful quantum hardware, we'll be able to slide that into existing enterprise systems. Next, please. So basically, we do have the same challenges at enterprise ML that we have today. And we've got some added dimensions with quantum, circuit optimization, hardware calibration, validating changes. Occasionally data may actually change the model as it changes in the external world. And then we need to be aware of our availability and uptime of hardware, especially remote hardware in this case. Next, please. And because 80% of the solutions that we develop for quantum really are still classical, we can look at what it takes to actually build, maintain, and deploy a machine learning model, and add the additional issues of circuit optimization and hardware integration, quantum hardware integration in with it as well. So as you can see here, we've got a list of things that are all involved in enterprise machine learning, and these will be the same issues that we need to worry about when we're deploying quantum solutions as well. So we need to be able to support the entire life cycle of a quantum classical solution beyond developing the algorithm. Next, please. So how do we get to this quickly? How can we really take advantage of quantum in enterprise now? So one of the approaches that we've been exploring, and we are exploring this with a few companies in both energy and in consumer goods, is our QEO approach. So really, we're looking at trying to boost existing solver solutions with quantum. And so the one advantage that this has is that we are essentially injecting new candidates into existing solvers. So it's less disruptive than it would be building a new system from scratch. And it really does act as a booster in this case. So for instance, we may have say something like portfolio optimization, all right, where we have a quantum generative model that we can use and use it to do combinatorial optimization. So an existing solver may be in place, and the systems are fairly mature. The outputs are known, and what we can do is add in additional quantum generated solution candidates in this situation. So this leverages the type of research that Sonika went over with us. And it also leverages the customer's existing systems that are already in place. And so this provides kind of a minimally invasive approach to quantum in the enterprise, which really cuts down on the amount of governance issues, validation, and all those invisible requirements that we see, because the existing systems have already been designed and are already deployed on infrastructures that address those issues. And we are simply inserting a little bit of quantum in this case, and boosting what is already there. And that's it for me. I don't know if we want to take any questions.
Hi there. Yep, a couple of questions have come in. The first question is there a clear advantage from the previous generation of IonQ computers for the generation of high resolution handwritten digits, or is this something to be proven in the next generation?
Chris and Eric, you want me to take that?
Yeah, sure. Yeah, go ahead.
So yes, so basically on the next generation of IonQ systems, you have many more qubits and much higher fidelity gates, right? And we know that quantum advantage increases with both of those things, right? Like basically the more quantum resources you have, the more advantage you have over classical computers. And we haven't done the experiment yet on the next generation of quantum computers, but I have no doubt that we're going to see even better results, and possibly go beyond even just generating digits to some of the real problems, real world applications that Chris and Eric were talking about.
And I guess I could just add to that, this is real results. These were experimental results on a real IonQ system that was the smaller system, and we're already seeing some advantage there, empirical advantage. So that's just going to grow as we get more entangled systems, if you will, larger amounts of qubits that will give us richer probability distributions. So that superset that I showed will get bigger and bigger. The quantum, the larger the quantum system that we're able to access because of the types of distributions that we'll be able to uncover.
Thank you. And then we've got one other question in for Sonika. Sonika, you said correctly that you need a distribution which is hard to sample from classically to achieve quantum advantage. Can you quantify how much of an advantage can be expected given the distribution?
Yeah, so if I understand the question correctly, it's kind of asking when you say how much of an advantage, right? So theoretically, we can make some statements, right? For instance, there are random circuits, right? And then for which the more quantum gates you can do with high coherence, plus the more qubits you have, the exponentially harder it gets for classical computers to sample from the same distribution, right? So as you increase the number of qubits, there's certainly an exponential advantage over there. Chris, did you have anything to add about that in terms of like how much of an advantage practically?
I think this goes back to the peeling of the onion. We know that if you're at 53 not fully connected qubits, in IonQ's case, they can be fully connected, as that nice graph is behind you showing. They can be more fully connected, so you have more entangled systems that are qubit to qubit more connected, if you will. So that connectivity and the number of qubits really will drive the math behind that. So we can say pretty certainly that you get up to 53 qubits. We've seen it experimentally with Google, and that was my first slide, that you're in a regime that you just can't do. It may take 10,000 years, or if IBM's right, 3 days to do just 53 qubits worth that are not fully even entangled in that system. or fully computational. And if we had 100 ions, which we're going to be approaching soon, I think, we're in a regime that's not just double that, because you add 1 qubit, you would double the computational value. So it's exponentially at a regime that is completely intractable classically. So it's not the point that on any data set, every data set, that this is going to be better, but we will be able to, by sampling over distributions that we cannot even begin to sample over classically, find correlations that are impossible, literally kind of impossible within real time to find in the data using a classical system. And that's pretty exciting.
Perfect, thank you. We've got one question for you, Christopher. It says, on your website, it states that you're pursuing fluid simulation. How far along are you with developing this? When would it be simulation suite that you can sell to an end user?
Mm-hmm. So this is what's kind of exciting about this near-term use of things. As Eric described, if you already have a simulator and you're already trying to optimize solutions and you have a classical solver, we can use this technique actually to look at the good solutions, the good simulations, if you will, or the good outputs. And when we do that, we kind of have, I kind of call it a quantum spy. I know that's trite, but basically you have a distribution seeker looking at the distribution of those correct or better outputs, if you will, right? And that's how this quantum enhanced optimization is working. We have papers available that we can share with you about this. So what you do, once you learn that distribution of the right answers, or the better answers, if you will, we can use what we showed you today to, now we have that distribution. So we sample off of that distribution solutions that the solver itself hasn't come up with yet. We've only had certain ones sampled to us, but now we know the distribution. So we can actually sample off of that same distribution solutions that the solver itself hasn't given us yet. So, and potentially you measure those against the same cost function, you get a better solution in that case, okay? So we can use our simulators that are doing that work with this as a kind of a shortcut or a booster, as we said. Now, the eventual potential of a fully fault-tolerant system, and IonQ has had some success in showing that the error correction mechanisms work on ions, and this is going to happen eventually when we get there. And that may be 5 years, it may be a decade, it may be a little more from now. We'll actually be able to brute force simulate those things better than a classical computer. And that's using a different type of fault-tolerant algorithm in a different regime. That will be really where this really starts to take off. But then we're in the thousands of qubits, for example, and fully connected and fully error corrected logical qubits types of regimes that we're talking about to get to that type of a system. So we're working on that. We're working with partners who are expecting those machines to come online in the 5 to 10 year timeframe. And we're working with partners in energy and other places who want to have access to those algorithms because they help develop them, so they don't need to pay someone else a license for them. So if you're on that kind of horizon where you think it's going to disrupt things, which it will, in 5, 10, I hate to put a time frame on it, when we do have these fault-tolerant computers, well, you might want to get involved now on creating those algorithms today from the theory and experimentation basis, because there's really no difference between doing that at 50 qubits and doing it at 1 million qubits. It's just going to get better and better when the hardware comes online. So that theory is going to be applicable. That's the work that we're doing today with those partners, with partners like IonQ.
Thank you. And then one question that came in during that one was, at what point can we use the QML at a real industrial scale?
It's ready. We're talking about putting this in production, in real production systems today. Because as I said, we're just boosting the classical solver. And the thing is, if you can get a little bit better solution, this isn't about being 1 million times faster or a gazillion times faster. If you're trying to detect cancer and you have a 3% better chance of finding the cancer, do you want to know that as the physician? Yes. So for those really, really important problems, having 3% better, 4%, even a 1% better chance, predicting a market crash or these kind of things, this becomes really important, or in an industrial system, if you can save 4%, in like an industrial energy system, the waste and the carbon and all of those kind of things, if you can get even those kind of numbers, it's better. So the beauty of this is that we can actually start thinking about putting these into production. Some of our customers are thinking about putting that in production very soon. And that's why the engineering stuff that Eric is talking about becomes really important. This can't be just an experiment type of thing. You need to have a production system that can actually deploy it.
Brilliant. Thank you very much. Now, have we got any more audience questions to come through before we go sort of to conclusions? Oh, we've got one question coming through. What do you think the key quantum hardware breakthrough has been in the past 12 months?
Wow. Sonika, do you want to take a stab at that one? 12 months. So we're beyond the supremacy experiment regime, right?
I think the demonstration of quantum error correction, right? The 16 qubit error correction demonstration that was done by Chris Monroe's group, who is one of the co-founders of IonQ. That was a really, fundamental step forward, I would say, in my mind. Yeah.
Yeah, I would agree with that, because that's the eventual promise of this, is to get to that fault-tolerant regime. I'd say even some of the experiments you saw today are a real step forward, because it's practical. That's a different kind of viewpoint. So if you're a business person, maybe the super science of the thing that's 10 years out isn't what's really exciting. What's really exciting to me is we're going to be able to deploy this stuff with real advantage in the coming months. And to me, that's really kind of cool.
Thank you. And then we've got one more question coming in. How do you entangle the qubits in the previous and new generation of IonQ computers? Are there any differences in terms of entangling gates in the quantum circuit?
Yeah, so at the theoretical level, they remain the same, right? The gate that's implemented, right? It's what's called a Malmer-Sorensen gate. So those are the same. However, on the new generation of IonQ computers, the entangling gates can be done with much higher fidelity or much higher accuracy. And as the end user, you would experience that as much higher performance of your algorithm, right? So that's one thing. And then the other thing is we also, and we published some results on this, we also made advances in terms of how stable the quantum computer is after calibration. So the duty cycle of the quantum computer has gone up quite a bit, right? So there previously you could, I forget the exact numbers, but I think it's almost gone up by 7 or 8x. Yeah.
Thank you. Do you think it is important to distribute the risk of betting on the right or wrong quantum hardware?
I'll give you my answer, Sonika. I really don't think it's a winner takes all type of thing. We don't have that even in computing architectures. Did CISC win or RISC win? I mean, well, ARM's still out there, but Intel's still got a big business. So, I don't think it's a winner takes all. I think we'll see that some of these architectures will be better at different things. I mean, it's obvious that ions have a higher rate of fidelity. The superconductors have a higher sampling rate. So depending on what your application is and what your algorithm is, you may use both in the same workflow, in the same solution. And you may use those and classical. You will definitely have a classical piece as well. So I really don't think in those terms that, okay, betting on one is really the answer. I think, if you had bet on ARM and Intel in a portfolio, you'd be doing pretty well right now.
Yeah, I would agree with that. I mean, it's I'm really an optimist about this space, and I think it's going to be worth trillions and trillions of dollars. And there's plenty of space for all the different quantum technologies, and it's a really exciting time. Yeah.
One more question's come through. What enterprises and end user verticals do you see most successfully implementing quantum hardware?
I mean, I guess I can take a shot at it. You're hearing like consumer goods is one that we talked about. Some of you may have read, in our Forbes article about that. We've published with BP, an energy company, and this is a horizontal technology. So it's not like, okay, if I'm in consumer goods, I can ignore this, and I need to be a quantum chemistry company to really take advantage of it. I don't believe that. Machine learning, as you've seen today in today's application, that works across all verticals pretty much. Having access to this precious hardware to use in production is not going to be probably your local ice cream chain store. To be honest, it's not going to be down market immediately. So that does kind of limit the kind of size of corporation that can interact with these systems and buy time on these systems, because it's precious time. But I think it's very horizontal. I think just about every industry will have some areas. Now, in the fault-tolerant regime, eventually, when we get into things like materials design and that we hear about a lot in the popular press and chemical design and that kind of thing, there are going to be some areas that are highly scientifically and R&D driven verticals that are going to be more disrupted by this than others. But I think in the near and medium terms, using these machine learning techniques and whatnot, I think it's going to affect everyone.
Thank you very much. That's all the questions that we've received this evening, lots of them. So I don't know if you've got any concluding remarks or if there's anything you'd like to share.
No, thank you very much. And thank you to my fellow colleagues here for presenting. And if you have any questions, we're up there at Zapata Computing at IonQ _ Inc. on our Twitter handles. You can contact us there and on social media if you have any further questions about this. So thank you for listening to us.
Thank you, everyone.